Alright, so in lecture 28 we're going to talk about the stereochemical outcome of the Diels-Alder reaction and the regiochemical outcome of the Diels-Alder reaction. So first we'll look at the stereochemical outcome of the dienophile. Remember, this is the dienophile because it loves the diene, and this is the diene because it has two alkenes. And so we don't have any extra substituents on the diene, we'll talk about that in a minute, but we have these substituents here on the dienophile. Notice about this bond here that these are cis. And so in our products, these are still going to be cis. Remember, in the Diels-Alder reaction, we have a mechanism that looks like this. And so we end up with new sp3 carbons, which can be chiral centers. So remember, the Diels-Alder reaction always gives you a 6-membered ring. You get a double bond in between where the diene was, and then everything else is sp3 hybridized. And so again, if you number these carbons, we got 1, 2, 3, 4, 5, 6. And so we have an aldehyde off of 5 and 6. So that would be these two carbons here. Alright, so these are sp3 carbons, and so we want to think about whether these are coming out towards us or going away from us. Again, since this is cis, these are going to be cis, so they'll both be on the same side. And we'll get a mixture of where they're coming out at us plus where they're going away from us. And so remember back from the spring that when we have a plane of symmetry between two chiral centers, we call these compound, and it's a mirror plane, we call these meso compounds. And meso compounds mean that they're the same thing. And so we take this compound and flip it over 180 degrees. It's going to look exactly like this compound. And so it gives us a mixture, it gives us a meso compound in this particular case. Alright, so now we're going to take a look when the dienophile is trans. So our dienophile is here, and our two aldehyde groups are trans to each other. And so the trans dienophile is going to give us a trans product. And so we get a mixture of these two things where the top one would be going away from us, the bottom one towards us, and vice versa in this compound. Remember that if we switch all stereocenters in a compound, then they are called enantiomers. And so we get a racemic mixture of two enantiomers in this type of reaction. So again, these are trans. Notice that these are also trans to each other. So it's pretty straightforward. Dienophile is cis, they're cis to each other. If they're trans to each other. Alright, so now let's talk about the stereochemical outcome of the diene. And so we'll just use a dienophile that doesn't have any substituents on it. And then we have a diene that has substituents on both sides. And so do these end up being cis to each other on our ring or trans to each other? So we see that this double bond right here is trans. And this double bond right here is also trans. Alright, and so when they're both the same direction, then they're going to be the same direction in the product. And so we get these two compounds here. And again, there's a mirror plane that goes through here, meaning that these compounds are meso. So if I take this compound and flip it over, it's the same thing as this. So a trans orientation about both of our alkenes and the diene gives us a meso compounds where these two substituents are on the same side. So think about this, that if you're looking at your diene, if this thing is pointing up and this thing's pointing down, then they're going to be on the same side of the ring. And then whatever's pointing in towards the inner part of the diene, which is two hydrogens in this case, are also on the same side. And so just keep that in mind, that when you're looking at the diene, these things are going to be on the same side, and the things pointing in towards the middle are going to be on the same side. Alright, so we just looked at a case where the diene has both of the double bonds in the trans position. Now we look at cyclopentadiene here. We look at this alkene. Both groups are going in the same direction, and so it's cis. If you look at this alkene, both groups are going in the same direction. So again, both of these are cis. And if they're both cis, again, they're going to end up on the same side of the ring. So think back to what I just talked about. This group here is pointing in towards itself, and so it's going to be on the same side. So we're going to get a mixture of of these two compounds. And again, there's a plane of symmetry here, a mirror plane. And so we take this compound and flip it over. It's going to be the same thing. So it gives us meso compounds. And our two groups are cis to each other. So our substituent off of this carbon, substituent off of this carbon are on the same side of the ring. All right, and then lastly, let's look at a case where one of the alkenes is trans and one of them is cis. So we look at this alkene here, this group's pointed up, this group's pointed down, and so this alkene is trans. This alkene, this group, and this group are pointing in the same direction, so it's cis. So in this case, we're going to end up having these groups opposite each other. Think about what I just said a minute ago. Whatever's pointed up here and down here are going to be on the same side, which is a hydrogen in this case. And then whatever's pointed in towards the middle is going to be on the same side, which ends up being those two groups there. And so we get a mixture of these two products where they are on opposite sides, as you can see from here. And then we also get the vice versa reaction. So we've changed both stereocenters in this case. And so these are enantiomers of each other. All right, so we've talked about the dienophile, we talked about the diene, and now let's talk about when they both have substituents off of these carbons and how the outcome of this affects the products that we obtain. So we know that Diels-Alder reaction gives us a 6-membered ring with an alkene in it. And so we're always going to have this kind of structure. And now let's think about it one thing at a time. And so we look at our diene. We see that this group and this group are pointing out of the diene, so they're going to be on the same side of the ring. Like that. And then also the other way around. All right, and then we look at our dienophile. We see that it's trans, and so we know that means that these groups end up being trans to each other. So they'll be trans on this ring in both ways, so we need to draw it again. so we get a mixture of where these two groups are both pointed towards us, but these groups have flip-flopped. In the same case over here. And so these are the four compounds that we would get out of this reaction. And so if we look at, let's see here, these two compounds here, they're actually the same thing. So if I take this compound and flip it over, these bonds will be coming towards me. This aldehyde is now going to be down here, so it's going to be pointing out. And this one's going to be now over here pointing back. So these two compounds are the same. And the same thing down here. If I take this compound and flip it over, it's going to be the same thing as this. And so actually, we only get two compounds out of this reaction, which would be these two shown here. Now, if we look at this, we see that we have not changed every single stereocenter between these two compounds here. And so we have changed these two stereocenters to the opposite direction. And so we call these kind of compounds diastereomers. So go back and review your notes from the spring if you've forgotten what meso compounds are, enantiomers, and diastereomers. All right, so let's take look at an example with a ring. And so we have cyclopentadiene here. This is our diene, and then we have our dienophile. As we just saw in the previous clip, whenever we get our four products, we only actually get two because two of those are the same as the other two. And so we can simply leave the outcome of our diene in the same direction both times. So we know that we always get six-membered rings. That look like this. We know that we're going to get two products when we have substituents on the diene and the dienophile. And we see that our diene here, this group is pointing in towards the middle of our diene, and so it's going to be on the same side. All right, and so we've drawn it twice now. Now we want to think about our dienophile. We see that this is cis. And so they're going to be cis to each other, either pointed away or pointed towards us. And so we get these two molecules shown here. Remember that when we have a ring, this is actually pointing up out at us, and so this is a top view. If we draw the side view, it looks like this. All right, so this point right here is this point, which I've indicated like this, so it's coming out at us. And then these aldehydes are pointing away from this group, so they're going to be going down. So it's going to look like this. Now we can draw the same thing for this molecule here. And so we have this type of thing, and then we see that these are pointing in the same direction as this point, so they're going to be coming up. So these are both pointing up now, or these are both pointing down. So you can imagine that when these are both pointing up, there's some steric clash between this point here, and so this is going to be your major compound, where they're pointed in the opposite direction of that point of your ring. We also call this point between our rings here and here as the bridgehead carbon. And that's just a name that we give for that position on the ring. Alright, lastly, we talk about these being endo or exo. And so you want to look at the substituents coming off of the ring and see whether they're going into the largest ring or into the smallest ring. So, if we look at this coming up, the ring that it's going into is the 1, 2, 3, 4, 5-membered ring. And if we look at these, they're going down into this bottom part of the ring. And so that's 1, 2, 3, 4, 5, 6. So these are going into the biggest ring, and so we call this the endo product. And then these are going out of the largest ring, and so we call it the exo product. Alright, so what about if our diene and dienophile are unsymmetrical, so we don't have two aldehydes coming off of here, or two methyl groups or something like that? We have to talk about the regiochemistry. And so you could imagine these two things reacting just like the way they're drawn. And so we always get this kind of 6-membered ring with an alkene. If we number our carbons, 1, 2, 3, 4, 5, 6. The 1 carbon's here, 2, 3, 4, 5, 6. On the 1 carbon is the methyl group. And then on the 6th carbon is the aldehyde. But you could also imagine the aldehyde flipping around and reacting the other way. And so now we have something like this. And so this is going to attack here, kick down, and come over here. So now if we number our carbons, 1, 2, 3, 4, 5, 6. On the 1 carbon we have the methyl group, and on the 5 carbon we have the aldehyde. And so these would be our two possible outcomes. And so this is actually the major product of this type of reaction, not this compound. And so we'll talk about why that is. Alright, so in the previous example I had a methyl group up here. I'm going to change it to a methoxy group. We know that methyl groups are donating, methoxy groups are donating, and so they do the same thing. Just using the lone pairs on the oxygen is going to allow me to describe why this is the outcome better so than using the methyl group. So if we draw out the resonance structures for the diene, I'm going to redraw it down here so we can clearly see those resonance structures. And so we can move our lone pair down and move this pair of electrons onto this carbon. Remember, your resonance arrows look like this. They're double-headed on each side. And so this is one of our resonance structures. Then we can move this lone pair down and move these onto that carbon. And so now these are our 3 resonance structures. So now let's draw out the resonance hybrid. So go back and review what a resonance hybrid is from the spring if you've forgotten. But a resonance hybrid is where we, any bond, single bonds that don't change in our resonance structures are drawn as solid lines. And so we see that we always have a single bond through here. So those are all of the bonds that never change in any of these resonance structures. Wherever you have a double bond in some of them, you want to do as a dotted line. So we see we have a double bond here, but not here. We have a double bond here, but not here. We have a double bond here, but not here. And we have a double bond here, except not here. And so it's going to be dotted all the way down, like that. And then you want to put partial charges on whatever atoms you see a full charge on in your resonance structure. So we see the oxygen gets this positive charge. This carbon has a negative charge. And then this carbon has a negative charge. And so this would be our resonance hybrid. And so we'll come back to this resonance hybrid in just a second. But let's go through the resonance structures of the dienophile. Alright, so we take our dienophile. We can move these electrons, no, let's start here. Move these electrons up to here. And so that gives us this resonance structure. And now we can swing these up onto here. And so we get these three resonance structures. So again, if we draw the resonance hybrid, all of the single bonds that don't change get drawn. And then anywhere we have a double bond in some structures but not in others get dotted lines. So we have a double bond here but not here. We have a double bond here but not here. And we have a double bond here but not here. And then wherever you see charges, those are going to be partial charges on your resonance hybrid. So we see a negative on the oxygen and a positive on this carbon and a positive on this carbon. So now we have our two resonance hybrid structures. And so let's take a look at how those line up in terms of our Diels-Alder reaction. So I'm going to draw back up our diene resonance hybrid. And so it looks like this. And now I'm going to also draw these where I flip this over, which gives us the, it doesn't give us the major product, and it's actually this setup. But we'll compare the two resonance hybrids. Alright, so now here's our two possibilities. They can either react via this way or via this way. And so we want to go via the route that has the most electrostatic interactions. And so whenever we draw the mechanism, we know that this carbon attaches to this carbon, and this carbon attaches to this carbon. These carbons don't attach to the dienophile, they just simply get a double bond in between them. And so we want to look at the charges on this carbon, this carbon, this carbon, and this carbon. So let's take a look at those. In this carbon we have a partial negative. This carbon we don't have any charge. In this case, this carbon has a partial positive. This carbon doesn't have any charge. And so if these two carbons are reacting with each other, they have the partial charges on them, they are going to have the most attraction, and our reaction is going to go via this pathway. Now if we flip it over, we have a negative charge here, which now needs to add to this carbon. And it doesn't have any kind of partial charge on it, and so there's not as much of an electrostatic interaction, and that's why our reaction does not go via this pathway, but it goes via this pathway. So no matter what diene or dienophile you have, you want to draw out the resonance structures, draw up the resonance hybrid, and then look at the charges on the carbons that are actually making the bonds to form your six-membered ring, and which ones match up correctly. So in this case, we have partial negative to partial positive. All right, and then I was going to talk about 24.6, which is the retro Diels-Alder reaction. So it's the reverse reaction where we take the six-membered ring and we go in the reverse direction. So we move this over to here, we move that to there, and we move this over to there. And so this breaks our bond here and our bond here, and gets us back to our starting materials. But this isn't very useful, and it has to be done at really high temperatures, and you have to have special setups and everything, so I'm not going to discuss it and I don't expect you to be responsible for the information in 24.6 on the retro Diels-Alder reaction.